So far, we've been able to maybe ignore frictional forces, or maybe our frictional force was given to us. And so today, we're really going to start looking at the relationship between friction and the rest of the system, and how the system we're dealing with is affected by friction. So there are two categories of friction, right? There is something called static friction and kinetic friction. Can you give me a guess as to what the difference is between that word static and kinetic? Static, what do you mean? What
stays the same and what changes?
Okay, static means it sits still, right? So it's an object that is keeping it sitting still, right? It's the frictional force that's keeping an object at rest, essentially. And then our kinetic friction is when something is moving. So the prefix kina means what? Move or motion, right? When we talked about kinematics, we're talking about objects that are in motion. So kina means objects in motion. Static means at rest. Okay. What do you think is the bigger force of friction? Static friction or kinetic friction? Okay, let me phrase my question differently. Is it harder to get an object started or harder to keep it in motion? Harder to get it started. So static friction is a little bit greater than kinetic friction. Okay, static friction is stronger. And it has to do with what we call the coefficient of friction. And we'll give those here in just a second. But we got to think about where does friction get applied? In what direction does friction typically get applied? Opposing the motion, right? Opposing the motion. And so if an object is moving to the left, friction is sliding backwards. Those things get a little bit tougher to deal with when we talk about objects that are slipping or non-slipping. We'll talk about that, things that are rolling. But friction is actually what allows things to roll, right? Rather than to slide. Okay, so if you kind of think about it in that term, right? Friction is what allows an object to actually roll instead of just slide down a surface, right? It's able to grip onto the surface and roll over rather than to just slide in motion. Friction is what allows our feet to move forward, for us to push on the ground and the ground push back on us to move us forward, right? Because if not, our feet would just slip and slide like we were walking on ice all the time. So that's what allows us to move objects forward, essentially. What are frictional forces dependent? Okay, in both our categories of friction, the more mass an object has, the harder it is to move. So friction is not only dependent on the mass, it's dependent on the normal force. Okay, it's dependent on the normal force. So I want you to give this a little bit of a test. I want you to rest your hand just lightly on your table. Rest it really lightly on your table and slide it back and forth. Not too bad, right? Not too bad. You can move it relatively easily. But if I increase the normal force, what will I do? Will I push down, or will I kind of pull up a little bit? If I want to increase the normal force, I would push down. So now try to move. Right? It's a lot harder, isn't it? Right? You're increasing the frictional force by increasing the normal force. Think of it as like you're smushing your surfaces together. Right? Even more. So they're coming into more contact, which increases friction. Friction is essentially dependent upon the two surfaces that are interacting. Okay, the two surfaces that are interacting. So like wood on carpet has a really high coefficient of friction. Okay, but ice on ice would have a really low coefficient of friction. Those two things are both really slippery, right? Okay, so that's what it says. The type of material and the surface are called the coefficient of friction, and they are given with a sign called mu. Okay. It's like a Greek letter, mu, and it looks like a U with a little tail on the front. Okay, that is the variable for coefficient of friction. Okay, the coefficient of friction does not have a unit. It does not have a unit. Okay, it's just regular, no unit attached to it. And it typically falls within the range of 0 to 1. Okay, we should not have coefficient of friction coming out greater than 1. Unless I make up a problem wrong. Okay, that happens. But typically we're looking for our coefficient of friction to be less than 1. So if you get a coefficient of friction in the single digits, teens, higher than that, that's a problem. Right? Probably means we did our division the wrong way. So I'll talk about that. All right. Our coefficient of friction are given with the same equation, okay? And I'm going to write out our equation a little bit differently, okay? All friction is given with this equation. Force of friction is equal to the coefficient times the normal force. That's how I want you to write it out. Coefficient times the normal force. Do you see that equation on your AP sheet? Okay, it looks a little bit crazy. Yours has it as an absolute value, and it's a less than or equal to coefficient times the normal force, right? But that's essentially what we're looking at here, okay? Frictional force is equal to the coefficient times the normal force. Coefficient times the normal force. Okay? When we talk about static friction, it does not change our problem at all. We're just saying that our static friction is less than or equal to our normal force times the coefficient. So we could have more than enough static friction than we need, right? Or just enough static friction. That's really all that that's saying. Okay, but this is the equation I would put on your equation sheet. If it is static friction or kinetic friction, we still solve it with this equation the same way. We're not going to use the greater than or equal to thing. We don't need to do that. Okay, we would just look at coefficient times the normal force. All right. Like it says here, kinetic friction is always directed opposite the direction of the motion, and static friction is what's keeping an object in place, so it is opposite of the applied force. So we could be pushing on an object, and if it's not moving, that static friction would be pointing in the opposite direction, right? Or it's keeping it in place. All right, here are some ideas about coefficients of friction and their differences. Again, each set of materials have their own coefficient of friction, and these will typically be given to us in our problem, or maybe we solve for the coefficient of friction, but it's not like we're going to have to go look at a data table to find it, okay? The coefficient of friction, I want you to see in every material set, which one is greater? Static or kinetic? Static, right? We already made that point. It's harder to get something started than it is to keep it in motion. So the static coefficients are greater than the kinetic coefficients, right? See how low this coefficient is for ice on ice, and rubber on concrete has the greatest coefficient of friction that's listed here. So that gets us to 1, but other than that, we want to be less than 1.
Why is glass on?
You're sliding a salt shaker to the right, giving it an initial speed of 1.15 meters per second. If the shaker comes to a rest with a constant acceleration in 0.84 meters, we want the free body diagram, the acceleration, we want all of the things. Okay, so let's look at our object here. It says we're gonna put it into motion. It's got gravity. It also has the normal force. In this scenario, are those two forces congruent? They are, right? Because my object is not accelerating vertically at all. Okay, and so I would have a normal force that's equal to my gravitational force in this case. We push the thing, but do we really care about the push anymore? We don't. Okay, so we're really just concerned with the fact that there is friction. So once I knew that my frictional force was the only force acting, I put that into my net force equation and solved for my frictional force. Now I can solve for the coefficient of friction, and we know that because we know force of friction is equal to coefficient times the normal force. So I can say force of friction 0.04 equals coefficient. And then what does the normal force need to be equal to in this case?
0.5.
Yeah, it would be 0.5 because FG is 0.05 times 10, which is 0.5 newtons. So my normal force also needs to be 0.5 newtons. And so my coefficient comes out to be 0.08. Does that fit within our range? Go ahead.
Why aren't we taking into account like the motion of it sliding and the force it takes to go?
So we're only looking at it after that force has been applied. So now it's just sliding, right? We're not applying a force the whole time that it is sliding. We put it into motion and then our hand's not touching it anymore. And so now we're just watching it like come to a stop. Yeah, that's a good question. If we applied a force the whole time, that would change our problem. But we just set it into motion, then we called it good. Okay, so sorry, does that coefficient fit within our range? Okay, coefficient, again, should never come out negative either. So if you get a negative coefficient of friction, you can't just say like, oh, we'll just make it positive. No. Go walk back your math and make sure we didn't have an error somewhere earlier than that, okay? And then if the salt shaker had more mass, how would it affect the answers to the question above? Would it affect the acceleration at all? Would mass affect that acceleration at all? It wouldn't. We didn't use the mass at all to solve for the acceleration, right? Mass doesn't go into kinematics at all. It would affect the friction, okay? So it would affect the frictional force. Would it affect the coefficient of friction? Yeah. I don't think so.
It would affect your normal force.
But if my frictional force changed, my normal force would change also, right? And so my coefficient is surface dependent, not mass dependent, right? The frictional force would be affected by a mass change, but the coefficient is only dependent upon the surfaces interacting. So it is not affected by mass. Okay, so we solved first for our frictional force of static friction. And now we looked at once the book got into motion, what was the acceleration of our object? And we used our kinetic friction coefficient there. Do we feel comfortable with this just subbing right into our problem? You know what I'm saying? Does that make sense? And are we good with the algebra of that? Instead of solving it separately and then bringing it in, can we do that all in one equation? Does that seem okay? Okay, good. I just want to make sure. Sometimes people like to solve them separately and then bring them together, but I like to put everything in one if I can. Okay, if the book was pushed with with 0.4 newtons of force to the right, and the book was not moving, what would be the force of friction on the book? Any thoughts on that one? That's exactly right. It would be equal, right? Our static frictional force would be just equal to our applied force because we wouldn't be able to put it into motion. So for part C there, it would just be equal 0.4 newtons of friction. And what direction would that be going? 0.4 newtons to the left. Yep, to the left. Okay, I'm going to have you try this last one on your own. And we're going to call it a day after that one, okay? Try this last one on your own. I'll give you a head start, and then I'll get up on the board here. Yes, you may. Make sure you start with the free body diagram each time. Okay, so in these ones, were we able to reason through that the force of friction and the pulling or pushing force would be equal to each other in both of these scenarios? Right? If we're doing just enough to get it started, that means we're applying just enough force to overcome friction, right? We're doing just enough. That means our push force and our frictional force would be equal to each other. So they equaled 2.25 in the first one. And I divided that by the normal force to get the coefficient. And then in the second scenario, it says once it's moving, they're going to be equal because it's constant velocity, right? Constant velocity means net force of 0. So my opposite forces have to offset each other, right? They have to equal each other. And so I got 0.0833.